Welcome back. This is part 2 of 3.1, our first day. We are talking about solving, rate of change, and slope. So let's start some stuff off with vocab. First thing you gotta remember about solving by graphing is that we are also dealing with linear functions. Welcome back to the class, f of x. Remember, f of x is just another term for y and can be substituted at any time. Now, parent functions are the most basic form of the function. Okay, we talked about it a bit in chapter 1. In chapter 1, we had it down as y is equal to x. Now that we're doing linear functions, same thing, but we're going to use the f of x notation. This is what the parent function looks like. Okay, it goes through the point 0, 0, and it increases up 1 over 1, up 1 over 1. So it has a slope of 1. It's written over here as well. Now, domain and range, welcome back to the table. Domain, remember, this is all values of x. And the range is all values of y. Can't read that. Domain and range is easy to find. You look at the graph, and for domain, you're going to look at the x-axis, in which case you notice that any x that you have, you can go down and there's the graph. Or you can pick another x and go up and there's the graph. So for the parent function of a linear function, the domain is all real numbers. Every single time. Even on other linear graphs, or linear functions. Okay, we mentioned that in the last video. For linear equations, the domain is all real numbers. The range follows similar rules. Any value of y, there's the graph. Pick another value of y. I go over, there's the graph. So the range for linear functions is also going to be all real numbers. This won't always be the case, but for right now, it is. Now, the thing we're talking about now is solving. So, the solutions to a linear equation is whenever, I'm going to move it like this, whenever the graph crosses the x-axis. Okay, so anytime the graph crosses the x-axis, you have a solution. These solutions have other names as well. You can either be called a root, a zero, or an x-intercept. These right here. So in our parent function, our solution to this graph would be, right here. So the solution would be x is equal to 0, because that's where the graph crosses the x-axis. And as I just said, the solution is wherever the x-intercept is. So that's what you got to gear your mind towards when you're talking about solutions, or roots, or zeros. You're looking for the x-intercept when y is equal to 0. So when we solve these things, we're going to use this exact same graph that we had last time. Okay, it's the exact same equation. There are two ways you can solve. Number one is algebraically. Okay, like I just said, the solution is whenever the graph crosses the x-axis or when y is equal to 0. So to solve algebraically, you just plug in 0 for y. So I have 0 is equal to 1/3 x plus 2. And now I solve for x. Minus 2. Okay. Now to get rid of the fraction, I'm going to multiply both sides by 3. And x, my solution is a -6. The second way you can do this is by graphing. So we already graphed this one in the last PowerPoint, so I'm just going to look at my notes here and regraph it instead of solving it out. But in order to solve by graphing, you could either create a table, you can go straight from standard to the equation or to the graph. Any of those methods work. 6, 4 is my next point. There we go. There's my line. And we can see that the graph crosses the x-axis at -6. So our x-intercept is equal to a -6 as well. This is why whenever you're graphing, it's very, very, very important to have straight lines, because otherwise you could miss your points slightly. But you could always go back and check algebraically. So if you think that -6 is your solution, you can always take -6 and plug it in to the equation, and you should get y is equal to 0. So y is equal to 1/3 -6 plus 2. -6 divided by 3 gives me a -2 plus 2. Y is equal to 0. It checks out. Okay, so if ever you doubt your graph, you can always check algebraically. Now, when we are finding our zeros, when we are finding our roots, solutions, all of those are the same thing. You're looking for the x-intercept. So on this graph, you're going to look for where the graph crosses the x-axis, and there it is. So the solution to this equation would be x is equal to 3. To find it algebraically using standard form, if you remember back to the beginning of last video, you would just plug in 0 for y. So 2x plus 4 times 0 is equal to 6. Now we have 2x is equal to 6, x is equal to 3. The graph and the algebraic equation both match, which they should. However, if you remember, not all graphs pass through the x-axis, as the graph on the right shows. For cases where you have y is equal to 3, notice how the line never crosses the x-axis, and it never will. Okay, so if it never crosses the x-axis, then it never has a solution, which means our solution, our root, 0, whatever you want to say, is no solution right here. This equation has no solution because it will never cross the x-axis. Moving on, the next thing we got to talk about is rate of change. Now, rate of change is the ratio, welcome back, ratios, that describes how one quantity changes with respect to another, namely x and y. How do x and y change in relation to each other? So whenever you're looking for the rate of change, you're going to look for the change in y divided by the change in x. Okay, think back to chapter 1 when we talked about slope, and I said how slope was always a fraction. This is where that fraction comes from. Okay, change in y over change in x. Another way some books might do it is this little triangle symbol. Okay, the little triangle symbol is known as delta. It's a Greek letter. In math, we often use Greek letters, but it means the same thing, change in y over the change in x. Let's go to some examples. Now, finding it from a table, you're going to look for the change, again, in y, and put it over the change in x. So what that means is I'm going to take 2 y's. Now, I can pick any of these 3 that I want, but I'm going to pick these 2, because as you know, I have a thing against bigger numbers. Not that you shouldn't use big numbers and that you should be scared of them, but I like to keep my odds of math mistakes down. Okay, divided by, and I'm going to pick the same 2 x's. So the x's go with the y's. Whatever 2 y's you pick, you got to pick those 2 x's as well. Okay, and then you just solve. So 156 minus 78 is 78. 4 minus 2 is 2. When you simplify this, which you can simplify further, you have 39 over 1. So the rate of change for this graph is 39 over 1. Let's go on to some other examples. Now, a useful trait of rate of change is that it is constant in linear equations. Okay, so if you were to have a giant table, or in these cases, medium tables, the rate of change should be consistent from every single point. You should be increasing or decreasing at the same rate for every single point, if it's going to be a linear graph. If it's not a linear graph, then you'll be increasing or decreasing just randomly. But so when you're trying to figure out if the function is linear, what you're going to do is you're going to see if the change is consistent. So from 1 to 4, this is plus 3. From 4 to 7, plus 3. 7 to 10, plus 3. 10 to 13, plus 3. So far, so good. Now let's check the y's, because x and y have to both increase or decrease at a constant rate. So this is a minus 2. Negative 8 to negative 10 is a minus 2. Minus 2 and minus 2. Both x and y increase and decrease at a constant rate, and so our rate of change is negative 2 over 3. Change in y over change in x. If that didn't really make sense to you, the other way you can do it is just set up the equation like we did in the last the last slide. So pick two y's, negative 8 minus negative 6 over 4 minus 1. Negative 8 minus a negative 6, so negative and a negative. This ends up being negative 8 plus 6. 4 minus 1. Now we have negative 2 over 3. Same exact thing. And you would just do the equation for each piece, for each block, the way you could make sure that the rate of change was consistent the whole time. And if you did the equation for every single block, it would be. So therefore, this equation is linear because the rate of change is constant. Now let's do the other one. I'll change colors. So let's do x's first. Negative 3 to negative 1, that is plus 2. This is plus 2 as well, plus 2, and plus 2. So far, so good. Let's do the other side. Here we have a plus 2. Oops, here we have a plus 4. That's no good. Here we have back again to plus 2, and then here we have again another plus 4. So the y's are not increasing at a constant rate. It goes from 2 to 4, 4 to 2, and back and forth. This, therefore, is an inconsistent rate of change, and therefore is non-linear. And if you wanted to do it the equation way, you could do 12 minus 10 over negative 1 minus a negative 3. And this would be 2 over 2, which would give you 1. But in order to develop a pattern, you always have to do two equations. Didn't do that on the last one because we had already proven it was linear. But for this one, I'm going to show you that you got to do it twice. So the next two would be 12 and 16. So I'm going to say 16 minus 12 over 1 minus a negative 1. On top, we have 4 over 2. And there we have our second answer. These two numbers are not the same thing. Therefore, the rate of change is inconsistent. Okay, so if you're going to do the method, this is personally my favorite one, where you just go down the side of the chart. It has to be the same number, the same constant rate of change on each side. X and Y increase or decrease at a constant rate. If you're doing the equation method, totally valid. You just have to do it twice to establish a pattern. At least twice to establish a pattern. All right. Another name for rate of change is slope. And we will be using this word a lot. I'll be using slope all the time. So slope describes how steep the line is, and is based on the absolute value of the slope. Okay, so when you're dealing with slope, the number means something, and then the sign means something. Those mean two different things. And we'll get into that in a bit. But the other thing I want you to know is that the notation for slope is m. Whenever we talk about slope, slope is equal to m. Now to find slope, you only need 2 points. That's all you need, 2 points. Because the equation for slope is y2 minus y1 over x2 minus x1. If you're having flashbacks to middle school, excellent. If you're not, this equation still makes sense because rate of change is the change in y over the change in x. You subtract 2 y's on top, subtract 2x on the bottom, which is exactly what we're doing here. Now, me personally, whenever I do these things, I always label my points. It just takes the risk of confusing the points down by a lot. So I'm going to say this is x1, y1, and here we have x2, y2. Now that I have my equation and my labeled points, I can just plug them all in. So m is equal to negative 2 minus 3 over 2 minus a negative 1. Negative 2 minus 3, this gives you negative 5 on top, and then this down here becomes 3. Therefore, m is equal to negative 5/3. And this would be your answer. So whenever you're looking for slope, whether you are given a table, whether you're given 2 points, whether you're given a graph, always remember that you only need 2 points. As long as you have 2 points in whatever form the problem presents them to you, you can find your slope. Now, as I said a minute ago, the number and the sign of slope mean 2 different things. Okay, so let's talk about that real fast before we go on to the next slide. Do this in blue. Whenever the absolute value of m is greater than 1, 3, 5, 2.5, anything like that, if it's greater than 1, then you're going to have a steep slope. Whereas if the absolute value of m is less than 1, you're going to have a shallow slope. Okay, so if my slope was, say, 5, random number, then I'm going to have a slope that looks like that. It's going to be really, really steep. Whereas if I have a slope that, say, is 1/2, then it's going to kind of do something more like that. Okay. Now remember, this is the absolute value of the number, so we're not taking sign into account. This is just the number. Before we talk about what the sign does, we need to talk about the 4 different types of slope, because there's not just one. Draw my, oops. The first slope is probably one you're very familiar with. This is when the line goes up. This is a positive graph, or positive slope. So whenever the graph is going up, your slope is positive. And this is a positive 5, positive 2.5, positive 1/2, anything like that. Whenever your graph is going down, then you have a negative slope. Okay, so over here, different examples would be m is equal to 1, m is equal to 5/3, anything like that. Over here, examples would be m is equal to a negative 5. Okay, m is equal to a negative 1/3. All negative numbers. The third type of slope is this picture, and this is a 0 slope. Okay. The things that create this would be all of your y equals graphs. Doesn't matter if it's y is equal to negative 5. Okay? It's still a horizontal line. It's never going to go up or down, so it is a 0 slope. And then last but not least, the fourth slope is undefined. And that's when it looks like that. This is an undefined slope. And these are all of your x equals graphs. So x equals 0, x equals 2, or x equals a negative number. Anything. It can be a fraction. We'll make this last one a fraction. Doesn't matter what the number actually is or even the sign. As long as it's x equals, it's undefined. And a quick and easy test that I like to talk about is my little dude on a bike test. So if I were to have a little dude and he's riding his bike, here's his bike, yay bike, and he's going uphill, then it's a positive slope. If he's on his bike and he's going downhill, then it's a negative slope. This dude's just chilling on an empty street, it is a 0 slope. He's just going down the street. If this guy is dying, falling off a cliff, because there's nothing else, he's dying, then it's an undefined slope, because our little dude is now dead. So whenever you want to know if you have a positive, negative, 0, or undefined slope, remember, little dude on a bike. All right, last but not least, some different common problems. Now we've already gone over the first one a bit. This is when you're asking for slope and you're given 2 points. So I'm just going to set this one up for you. You have m is equal to y2 minus y1 over x2 minus x1. Again, I like to label my points. Any trick I can do to reduce my math errors are my favorite. And now that I have everything labeled, I'm going to plug them straight in. So I have m is equal to 5 minus 0, 1 minus a negative 2. Okay, this is actually simple, so we'll go ahead and finish solving. So m is equal to 5 over 3. And that's my slope for this graph. But the next common problem that you'll see a lot is when you're asked to find r. So you're given a point, you're asked to find a line that goes through these 2 points with this slope, only we don't know what the full point is. Now the setup for this is the exact same thing. Our equation is the exact same. Doesn't change. So I'm going to go and label my points, reduce my error. This is still x1, y1, this is still x2, and r is my y2. And then of course m is 1/3. So now I'm just going to take all these pieces and plug them into my equation. So I have 1/3 is equal to r minus 4 over negative 5 minus 1. Now that we have our equation, we're going to solve for r. So 1/3 is equal to r minus 4 over negative 6. In order to get anything out of the denominator, I need to multiply both sides by the denominator. So times a negative 6 times a negative 6, which gives me a negative 2 is equal to r minus 4. And then add 4 to both sides. And we have that 2 is equal to r. So our missing point that would complete this scenario of a line that goes through these 2 points with 1/3 slope would be negative 5, 2. All right. This is the end of the part 2 video. If you have any questions, please ask me in class, and I will see you next time.